Our next presentation will introduce us into strategic garment design for energy harvesting from the human body. Please welcome Amanda Myers, Laboratory Manager of North Carolina State University, College of Textiles, United States of America.
Good morning. Thank you all for coming to listen to me talk, even though I know the show has a lot to offer and it's very exciting. But my name's Amanda Myers, and I wanted to talk to you today about strategic garment design for energy harvesting from the human body. And so briefly, I want to talk about what exactly strategic garment design is, give you a little bit of an overview on different energy harvesting mechanisms from the human body, but then want to take a deeper dive into thermoelectric energy harvesting in particular, and how we've used that to generate different knit structures and knit designs for creating an energy body map of yourself. So strategic design already exists. And you see, especially in the textile industry, a good example of this would be this parka or puffer jacket. It is designed to be worn by a skier or a snowboarder. It's designed to be worn in a specific environment. So essentially, strategic design is designing based off of a specific use case scenario. So how do we then translate what we already do for different types of sports and other textile uses to electronics? Well, there are several overlapping needs. There are some general themes that we have. One of which is electronics need a power source. They need, and this is typically seen in the form of a battery. They also have very specific defined operating conditions. Typically, you see a computer in a room held at room temperature with very consistent environmental conditions. They also have engineered circuitry. So each computer is designed to perform a specific task, and they're engineered to do so. Garments have a fundamental pattern that you use to build from the ground up. You also see that they have a defined fabric for a specific use, such as a nylon or polyester for a sport fabric versus a wool, so for a sweater. An interesting thing that is a little bit different here is that they need to be reusable and washable. So this means that whatever we do in our integration strategy for our design, we need to make sure it is robust enough to withstand a wash cycle and repeated use and wear. So I mentioned the battery. Now, your body is a terrific source of energy. In fact, the average person has about 384 megajoules of energy. Now, we expend that in different ways. A lot of it is used to keep our core body temperature at 37 degrees centigrade, keeping our used in movement and our daily activities. And I like to think of ways that we can harvest this energy in either an active way or a passive way. Now, active energy harvesting, I define as energy harvesting that requires some type of input. So, for example, a piezoelectric, where you have to bend a material, or say, for example, a triboelectric energy harvester, where you have to monitor the distance and the relation of two materials to each other. Then on the other side, there's passive energy harvesting, or energy harvesting that you wouldn't have to put any thought or extra thought or effort into. For example, body heat. I don't think about how much body heat I'm producing on a daily basis. It's way in the back of my mind. But it can also be used, you're constantly putting off body heat. It is a continuous source of energy. Also respiration. Now, even though it's also piezoelectric, you're always breathing, hopefully. And you can use that as well to harvest some small amounts of energy. So let's take a deeper dive into thermoelectrics. So a thermoelectric device is a material property based on the Seebeck coefficient, which is how a temperature difference is able to generate an electrical potential. Now, the greater this temperature difference between our hot side and our cold side, the larger our electric potential will be. So in an ideal scenario, we want to maintain this temperature difference and prevent reaching a thermal steady state. One way to kind of look at this is at the thermal circuit. So you have a series of thermal resistances that all play into how heat transfers to your thermoelectric device, through the device, and away from the device. Now, this is a pretty simple diagram showing how the thermal resistance of the body is in series with the TEG and with the resistance as you transition to the air. But then when we add textiles, this gets significantly more complex, as you have to take into account the heat transfer through the textile and other heat transfer mechanisms within the textile itself. So a couple variables that I want to talk about that we need to consider in strategic garment design. And probably the most important one for energy harvesting from the human body is the human body. So you are a great source of energy, and this kind of shows a heat map of exactly where on the body you can expect to find the most heat that you're putting off. And you can see that it's right around the core, so where your core body functions are and where your core organs are. Now, on the extremities, you see a little bit less of a temperature difference there. And so we've done some human trials in developing kind of this map of the body. And here's an example of the garment that we designed and where the locations of our thermoelectric devices were to characterize them. Most of them were located around this core area where we would get most of the heat output. We also integrated one on the wrist. And the reason why we did that is for variable number 2, movement. When you're moving, you generate convection, which helps maintain this temperature difference, because you're consistently removing heat. The faster you move, the better you're able to maintain that temperature difference. Now, here we see, if you're running constantly, if you follow that green slope there, you see a pretty consistent increase in the amount or the rate at which you're harvesting energy. As you slow to a walk, it decreases. You have less convection. But when we rest, it almost goes completely to zero, meaning we're reaching a thermal steady state. We're not removing the heat from the other side. Typically, throughout our days, we're not in a constantly moving situation. So how can we look at improving and maintaining that temperature difference even while we're at rest? While we do that, we also have to look at the environment. So how does the outside and ambient air play into that? Well, if we look across here at how much power we're generating, and you look at how much it varies across the temperature axis here, with changes in environmental temperature, or that hot side or the cold side, you don't see a lot of variation. Instead, you see a very significant change here with the convection. Now, this tells us that convection is a very important part of maintaining that, of preventing the thermal steady state. Additionally, when you're running and you're moving, you also tend to start sweating, meaning you also have evaporative heat loss. Also, it contributes to improved energy harvesting efficiencies. The last variable I want to talk about is the material. So we talked about having this textile circuit, or the thermal circuit that has the textile in it. So we compared two different very basic knit structures, one a jersey knit and the other a rib knit. You can see with the jersey knit, we have a very thermally saturated environment, so we're not going to be harvesting a whole lot of energy. But with the rib knit, it's a less dense fabric. We have a more loft, meaning there's more air within the fabric itself. So we're kind of creating this more insulated environment, and it helps to direct that heat flow towards the energy harvester, where it can then be used to improve our energy harvesting. So in our design, we decided to choose where we integrated all of our thermoelectric devices. We used a rib knit structure as opposed to a jersey knit. So here's an example of what the finished product kind of looked like. So how did we integrate it? Well, I did mention that thermal resistance in between the body, and we want to keep that as low as possible so we get as much heat flow into the thermoelectric device as we can. So in order to do that, we added a heat spreader, so a conductive material, nickel copper fabric, to increase that area and to promote heat flow to the TEG. We then sandwiched it between some thin layers of thermoplastic polyurethane, or TPU. This is to help with that mechanical robustness so it can withstand wash cycles and be used repeatedly. So I mentioned that humans aren't going to be sitting or standing and maintaining being stationary all one day. So how do you analyze the human scenario? You can't really do it on a laboratory benchtop. So how can you recreate what people might be, the different environments people might be exposed to? Well, we had a series of activities, running, walking, resting, in either indoors or out of doors. Now, while participants of our study were doing this, we were monitoring several things at each location of the thermoelectric devices. One was we monitored movement with the accelerometer and gyroscope. We monitored external temperature and humidity, as humidity does play, again, a significant factor into how our body responds to the temperature. And last, we also monitored how much power we were actually generating. Let me take a look and explain what we're looking at. So in our core areas where we integrated thermoelectric devices around the torso, so the front, the back, and the side. On the side, we see we have a maximum power generation of about 5 microwatts, which is the worst out of all of these. That's because in this microclimate here, even though you might have convection from your arm, it's going to thermally saturate fairly quickly. On the torso and on the back, we see better power output. The torso, you see a very traditional kind of what we expect to see. Lower temperatures, lower ambient temperatures, and higher velocity, and that's where we're going to see our max power. On the back, you see a little bit more of a spread on the maximum power generated across the velocities, meaning that it might be more suited for other types of activities, such as walking, maybe less strenuous activities that don't generate as much convection. On the wrist, while we have a lot of convection, as you saw from that thermal body map, there's not a lot of heat that's coming off of your body right there. So even though you're generating a lot of convection with your movement, and you see that at the maximum, it's still not the same magnitude of power that you would get from your core. What I found most surprising, though, was one of our best locations was on the shoulder. And the reason why I'm saying it is the best location is because our maximum power is distributed at relatively low movement velocities, so they're not requiring people to move all the time. And it also spans a range of temperatures, meaning even if it gets warmer or so, you would still be generating power. Why is that? Well, it goes back to that thermal contact resistance. When you integrate your device on the shoulder, the gravity is helping you. Typically, our garments will almost always have some kind of shoulder. That's where they rest, and that's what holds our garments up. So that's assisting us in maintaining that contact with the body and lowering that thermal resistance to heat flow. So this was a little bit of an overview on kind of how we design strategic for thermal energy harvesting. But where else would you want to see strategic garment design? Sensing. When you move around, a lot of biomonitoring requires sensors that maintain good contact with the body. Unfortunately, because they're integrated into textiles, they move with the textile and lose that contact. So doing so introduces a lot of electrical noise into a signal and can mask what we're actually trying to sense. So we did a series of movement studies to identify the areas where garments are going to be experiencing the most, say, displacement. And what we did was we created a series of panels to help absorb some of that displacement while isolating the sensing area where we need compression. So, for example, we used a mesh structure as it would absorb much more of that energy, and then a compression around the belt or around the torso where we have all of our sensing. And that way we were able to not only maintain compression up against the body, but help kind of isolate that region from movement from your arm. So strategic garment design is relevant in not just, designing parkas or integrating energy harvesters or sensors. So, but what's next? Well, using our knitting, we're able to customize the microclimate that surrounds each of our energy harvesters to help promote that heat transfer. Lastly, we also want to look at more different types of energy harvesting, so not just that thermal energy harvesting, because that's on its own, that's not enough to power things. So how do we integrate other methods of energy harvesting as well and do a direct comparison in these same scenarios to see exactly how much power we can generate? With that, I would like to thank you for listening to me. I would like to acknowledge the principal investigator of our group, Dr. Jesse Jur, and none of this work would have been possible without our amazing students and our funding from the ASSIST Center, a National Science Foundation Engineering Research Center. Thank you, and I would be happy to take any questions.
Any questions? Yep.
Thank you. Did fiber have any impact?
Yes. Fibers themselves have different thermal properties. So, for example, we did all of our studies with a polyester fiber. We have not done any with natural fibers such as cotton or wool, but they're also very insulating materials and could help and could assist in promoting that heat transfer.
Hello.
Hello.
Is there any commercialization of this activity, of this research?
Not at the moment. For some of the sensing, there's a little bit of commercialization, but right now we're generating more of this energy body map, which isn't necessarily commercializable, if that's a word.
Have you tried this with the inner garments, the inner wear garments that we wear, so that is more close to the body? Because normally everywhere in hot countries or in any country, they wear the inner wear also. So if that could incorporate in your study, so I would like to ask on that.
Yeah, right now we have just a single layer, and the reason for that is we want to maintain that temperature difference. So we want to have our device exposed to the ambient air, and having another layer over that would significantly decrease the amount of energy we're harvesting because you don't have that convection that would remove the heat.
Did you use regenerated fiber like bamboo or tencel?
I'm sorry, can you repeat that?
Did you use regenerated fiber like bamboo or tencel?
No, we haven't. We've only, like I mentioned before, we've only done this so far with polyester, but we are continuing to explore these different fabrics, different structures, to kind of create a more generalized kind of idea of what you can use, if that makes sense.
Have you tested the durability of your system? The durability, wash testing, for instance?
We haven't done a whole lot of wash testing. While we were doing the trial, we did wash the shirt in between participants. So I can tell you it withstood about 7 washes or hand washes. But we haven't done a full wash testing cycle yet.
I want to know when you're testing, do the testing, do you dynamic testing or just indoor testing?
No, we have our participants do these activities both indoors in controlled environments and outdoors, so we can see how, because we're not able to control the outdoors whatsoever, so it helps to be able to characterize what someone might be exposed to in a wider variety of environmental conditions.
And last question, maybe?
What kind of thermoelectric system are you using?
Right now we use small commercial devices. They're layered. They're a rigid ceramic, so they're about 6 millimeters by 10 millimeters that we're using. So they're designed right now for and optimized for cooling purposes rather than energy harvesting purposes. But yes, we use layered thermoelectric devices.
Okay, thank you very much, Ms. Myers.
Thank you.